Hi, this is Jeff Lockridge. Today I'll be talking about the Elastic Load Balancer Sandwich architecture. This is a highly available, fault-tolerant architecture that you can use to protect your workloads in the cloud with firewalls. There are several ways to get firewalls into the AWS VPC. In a previous video, I talked about one mechanism, and that's including an elastic IP address on the firewalls. That design is limited in how it can scale, given that it relies on EIPs, which have a limited number per region. I also covered in a previous video VPC ingress routing. This feature was introduced in 2019. It is a way that you can force traffic to go through a firewall and then include public IP addresses in the private subnet. The Gateway Load Balancer was announced last year in fall 2020. That's a very advanced way to force traffic through a firewall. I will probably cover that in a subsequent video. Today, I'll be discussing how we can use the ELB Sandwich architecture to force traffic to go through a firewall in your VPC. The objective here is to perform inbound and outbound inspection using stateful firewalls. We want to do that in a highly available and fault-tolerant way. The workload that we're trying to protect is a web service. Let's say you operate in a highly regulated industry. Perhaps you're bound by PCI DSS. We'll say, for the sake of argument, that a web application firewall, or WAF, is not going to meet your requirements. You need to have a stateful firewall. Let's say that you offer this web service using Apache 2 as the web server software. We're going to use VIOS in this case for the stateful firewall. VIOS is an open source router. This could alternatively be Palo Alto, Fortinet, or any of the other major firewall vendors. The reason why it's called the sandwich architecture is that the firewall is sandwiched between two load balancers. You have an outer load balancer and an inner load balancer. The outer load balancer could be a network load balancer or an application load balancer. Here we're going to use the network load balancer. In this architecture, the NLB terminates the encryption, the TLS session, so that the firewall has full visibility into the full packet payload. I recommend using Amazon's ACM service, which simplifies the management of certificates. It also does automatic renewal. Now, at the firewall layer, the best practice would be to have auto-scaling. So you have auto-scaling at both the firewall layer as well as the web service layer. In the example today, and in the Terraform that will accompany this video, I'm not going to do auto-scaling. We'll have static web servers and we'll have static firewalls. Two firewalls, one per availability zone. The network load balancer will be instantiated in the public subnet, as will the firewalls. The inner load balancer will be an application load balancer that's instantiated in the private subnet. When the NLB receives a packet, it will pass that packet through without modification. The firewall will perform destination NAT to direct the packet to the inner load balancer. The firewall performs both source and destination NAT. The reason why it does source NAT is to ensure symmetry. With stateful firewalls, we need to ensure that the path to the web services mirrors the path back, otherwise that packet would be dropped. And doing that source net is how we can ensure that the path back will use that firewall. The inner ALB will send packets to either availability zone. Don't forget, you can't disable cross-zone load balancing for the application load balancer. The web servers will be listening for HTTP traffic. You don't have to worry about managing certificates on those web servers. The web servers will process the traffic, send traffic back to the ALB, which will in turn send traffic back to the firewalls and then out to the internet. Let's talk about a packet walkthrough. In this architecture, you'd want to associate a CNAME for your fully qualified DNS to the DNS name of the NLB. Alternatively, you could use IP addresses. In the case of the NLB, those IP addresses are fixed, so that is another option. Now, before we get to the packet walkthrough, I do want to correct one thing I said mistakenly earlier in this video, is that packets are not unchanged when they hit the NLB. When they hit the NLB, there is a destination NAT. All right, let's take a look at a packet from the internet destined for one of the web servers. The packet hits the NLB. It'll have some internet source address. The destination address will be an IP address, a public IP address on the NLB. The NLB will do a destination NAT to the untrusted ENI on the firewall. In this case, it's 172.17.0.50. The source address will remain unchanged. The firewall will do both a source and destination NAT. For the destination NAT, the new IP will be the IP address of the ALB in the same availability zone as the firewall. The source address will become the trusted ENI IP address of the firewall. The packets hit the ALB. The ALB will do a destination NAT to the IP address of the web server. The packet has reached its destination. Let's take a look at the return path. The packet leaves the web server, hits the ALB. The ALB sends it towards the trusted ENI of the firewall. The firewall changes the destination address back to the original internet destination IP address. The source is the untrusted ENI of the firewall, hits the ELB. The ELB does its thing and translates the addresses back to the original. I want to point out one aspect of this architecture involving the visibility of the original client source IP address. The web servers will not see that original source IP address because of the various network address translations that are happening. If you need that original source IP address, you'll have to modify the architecture. Now, why can't they see the original source IP? Why isn't it in the X404 header? Well, the NLB does not insert that, nor does the firewall. You'll have IP addresses in the X404 header, but you will not have the original client IP address. Swap out the NLB for an ALB if you do need visibility into the client source IP address in your application. In that case, the ALB will insert that X404 header, so you will have the original client IP available in the X404 header. There'll be a comma-separated list. I believe the first entry will be the original client source IP address. I've had clients who do need that for some kind of reporting, some kind of application layer blacklisting. So if you do need that visibility, use the ALB as your outer load balancer. Now, if you use an ALB as your outer load balancer, it will perform a source NAT, so your firewall will not see the original source IP of the packets. That is a drawback. You'll need to have some kind of decision making based on the X404 header, which some firewalls do not have. Palo Alto recently has added some abilities to make decisions based on that X404 header. Whether you use an NLB or an ALB as the outer load balancer, I want to point out one thing that has to do with the inner load balancer in either design. As you probably know, the IP address of an ALB, one per availability zone, can change as the ALB scales in and out. I've used VIOS for the firewall, as I've mentioned, in the Terraform that accompanies this article. In that setup, if the ALB changes IP address, routing will break. You'll need some kind of Lambda to check the status of the ALB. If a change is detected in the IP address, the Lambda should go in and make an update into the firewall's routing table. Now, some of the commercial firewall implementations, such as Palo Alto, allow you to route to a fully qualified domain name as the next hop. If you can do that, you don't have to worry if that IP address changes, because when it does, it'll automatically update that next hop IP address. All right, let's check out the Terraform. In the Terraform, I'm using Vios. I've included an AMI from the community AMIs for US West 1. I recommend you launch it in that region. For production workloads, I strongly recommend using Centrium's AMI for Vios. Centrium is the company behind Vios. You can pay a very small hourly fee to use the official AMI. I would do that. It's a very worthwhile product. All right, let's look at the vars.tf file. You can customize a few things here. First, add your IP address to the management prefix so that you'll be able to SSH into the Bastion host that gets set up by this Terraform. This is not my actual IP address. I've concealed it using a tunneling service. Include your IP address here. Also, you'll need to have an SSH key that's defined in that region. In my case, my SSH key is called Jeff key. The firewalls are set up in the firewalls.tf file. In the instances file, it instantiates the web servers as well as the Bastion host. NLB sets up the NLB. The ALB file does the same for the inner load balancer, the ALB. You can clone the Terraform files using the link provided in the YouTube description. Once you do cd into that directory, we'll do a Terraform init. This will download the appropriate modules. This will take a few minutes. Okay, now that's downloaded. You can make those changes to the vars.tf file that I mentioned. Now we'll run a Terraform plan. This takes a while. I'm going to pause the video. All right, that completed. We'll follow that command up with a Terraform apply. I'm going to use the auto approve flag so I don't get prompted yes or no to proceed. This also takes a while. I will pause the video. Okay, that is complete. You can see a lot of output. That's intentional. I included a lot in the output.tfs file. There's a problem with the Vios AMI that I used. The user data is not working. There's some manual configuration that's required. That's why I outputted some configuration. Let's take a look at the internal load balancer. I'm going to copy this DNS name. Let's get that right. Let's do an NS lookup. All right. As expected, we see 2 IP addresses, one per private subnet. You can see the 100 and 101 subnets. We'll be using these IP addresses in the Vios config. Also, you can see here we have the NLB FQDN. This is what you'd use in your CNAME. Let's do a look up here. We will see 2 Amazon-owned public IP addresses. Now I've SSH'd into the Bastion IP address, which was also in the outputs of the Terraform apply command. As I mentioned, there's some final configuration we have to make. I'm going to SSH into the 2 firewalls. configure. I'm going to paste that configuration that you saw in the outputs. Now, note I've filled in for the NAT the IP address in availability zone 1 for the ALB. Going to do a commit, exit. We'll do the same. Now we'll SSH to the second firewall. Drop into configure. We'll paste the second firewall configuration. Do a commit. Exit. Now we'll go to the AWS console to verify the configuration. If things work properly, you'll see 2 firewalls, 4 web servers, and the bastion we were just in. Now, here comes the moment of truth. You'll see target groups for the firewall that are associated with the NLB. Those have a TCP listener. Let's check those. Actually, let's check those second. We'll check the web server target group. And we see healthy. That's good. Let's check the target group for the NLB. Healthy, healthy. This has the end-to-end health check. This proves that the configuration was successful. We have a fully functioning architecture, the ELB Sandwich. Time to visit the web service. We're back in the AWS console. We're going to get the FQDN associated with the network load balancer, the outer load balancer. Copy the DNS name here. Go to my other browser, type it in. There we go. We see one of the web servers. Let's see if I can get it to, there we go. Going back and forth. Looking good. Now, let's try to get it to block my IP address. All right, we've reconnected to the bastion. Going to SSH. This time we want to SSH to the trust IP because of the way we're doing NAT on those firewalls. Okay, we're in the firewall. We're going to add a null route for my IP address to prove that the firewall can block. So let's do this, set protocol static route. Set the next hop. Let's see my options here. Black hole. Commit that change. We'll go to the other firewall at 101, 110. We'll do the same thing. Static null route. Commit that change. Let's go back to the browser. Try to connect again, and we can't. We can go back to here, delete that. Here. We're going to delete that static route. Back to the first firewall. Commit, exit, go back to the browser. We can connect again. So there you go. Fully functioning web service where you can block IP addresses on the firewall. In this video, I've showed you how to implement the elastic load balancer sandwich architecture. If you have any questions, please feel free to reach out. If you'd like our help in integrating Palo Alto or Fortinet firewalls into your VPC, please contact us today. Thank you.